the column wise all element addition to get P of y1, P of y2 and P of y3. Then hx value, what you have obtained, check out. Hx should be 1.96 bits per message. Have you got this value? Hy is 1.94 bits per message. Check out your P of y1, P of y2 and P of y3. They are with 0.3, 0.5 and 0.2 value. Then h of xy, what was the value? 2.49 bits per message. Okay.
Yes,
and h of x by y? In two ways you can 1.04, no? Roughly. Okay. Then h of y by x, how much?
0.53.
0.53. And that next topic we are starting as the parameter which is related to the channel itself. And the channel parameter, we are calling that as a mutual information. Until we have seen the parameters of information, then we have gone for entropy, then we have seen the concept of self-information, then we have seen the different variety of entropies, their derivations and numericals based on that. So the next concept of mutual information we are going to start today. So generally, this mutual information tells us about what is the variation in uncertainty of that event. What is the variation in the uncertainty of that event? Because at transmitter, it may be uncertain that always I'm going to transmit my first symbol. In the same way, at the receiver, there is uncertainty that first transmitted symbol always I will receive as a first received symbol. And that's why here on the channel, we have to check for what is the actually mutual information between the transmitter and receiver. And according to that mutual information, we have to go for checking the amount of information which has got transferred from the transmitter to receiver. And so this mutual information will be defined as the measure of amount of information that can be obtained about one random variable by observing the another. So it is what? Amount of information, but it is obtained about one random variable by observing the another. So if suppose I am considering the random variable at the transmitter. Transmitter is indicated by capital X and the random variables related to the transmitter will be indicated by xj's. Similarly, I am seeing the another terminal or another variable at the receiver, and that receiver variables we are indicating with yks, sorry. And that's why here we are going to define the amount of information when I'm going to obtain either a transmitted variable, but for that I have to observe first the received variable, or I can say that I am going to see the received variable, but for that first the transmitted variable has to be obtained. And that's why in the communication we are saying that it can be used to maximize the amount of information which is shared between the transmitted and the received signals. That's why the mutual information will be measure of both transmitter and received amount of information. Previously, information we were only representing as I, and the joint information never we have represented, but here the mutual information can be said to be the joint information also. And to indicate that mutual information, we are having I, which is the information indication, but in bracket, instead of either x or y, we will have both of the parameters of x and y, which will be separated by a semicolon. So whenever this notation we will observe, I of x semicolon y, there we have to understand that it is the mutual information parameter, because information is simply associated either with x or with y. But for mutual information to be understood, the two different variables we are going to need. And two different variables will be one from transmitter and other from the receiver. And that's why to indicate the mutual information variable, we are using the symbolic representation as I of x semicolon y. And as I have told you, this mutual information is a measure of uncertainty. And that's why here we are going to have a subtraction for finding out the ultimate uncertainty in happening of the event at one end and getting that event to occur at the another end. So let's check for that. So we are starting from the transmitter. So at the transmitting end, the information which is conveyed by x will be given by h of x. And this h of x will be your initial uncertainty. But when I'm observing the y is present at the receiver, that means we have seen the symbol has been received, but what the symbol we have received, that has been already should be transmitted in the form of x. So here, to understand the uncertainty related with the received symbol which is transmitted as a x, we have to take the conditional entropy of h of x by y. And that's why the mutual information will be stated as initial uncertainty minus the final uncertainty. And in this situation, initial uncertainty will be given by entropy related with the transmitter, because we are starting with the process of transmission. And the final uncertainty will be seen at the receiver end. That means first the reception has to occur, but that reception has occurred for which symbol, that we have to check. So the conditional entropy will be needed over here, and that conditional entropy will be h of x by y. So in short, what we have said, mutual information is nothing but the amount of uncertainty to be conveyed from one end to another end. So as like information, for the mutual information also, we are having the different properties. The first property is telling us the similarity, and that similarity is either we are starting from the transmitting variable towards receiving variable, or we are starting from the received variable towards the transmitted variable. In both the case, if I am going to measure the mutual information, that will be the same value. Previously we have seen the equation for what? I of x semicolon y, which says that it is h of x minus h of x by y, because it is related with the transmitter. But if suppose I am now stating the equation of I of y comma y semicolon x, that means I am seeing first the receiver end, and from the receiver end we are observing towards the transmitter end, and that equation of I of y semicolon x will come out as h of y, because here first the received uncertainty has to be seen minus it will be h of y by x, because after getting the transmission to be done, the reception we are going to observe, and that's how these two values will become equal. And this is the said property of the mutual information, that either I see from the transmitter end variable towards the receiver variable, or I am seeing from the receiver variable towards the transmitter variable. the amount of mutual information or the uncertainty variation should lie same. Should lie same. That is what the meaning of this first expression, which is giving the property of mutual information. The next property of mutual information is what? I of xy value is always greater than or equal to 0. Next, just I have mentioned here, that is I of x semicolon y. It can be written as h of y minus h of y by x. And why I am putting here I of x semicolon y? Because here in the first property we have stated that these two values will be same, and that is the property of mutual information. Even though we have written this expression part, which is giving the value of I of y semicolon x. In the part of this I of xy representation, which previously we have mentioned in terms of marginal entropies and the conditional entropy, that can be replaced with the help of two marginal entropies along with the joint entropy representation. So in previous two mutual information equation, we were seeing only the marginal entropy and the two conditional entropies, while in this last expression we are observing along with these two marginal entropies, the joint entropy is present. So how it comes out, and what is the derivation of this I of x semicolon y is equal to I of y semicolon x, that we are going to see in the next part of our slide. So here we are starting with again the event occurrences at transmitter end and at the receiver end. So already we have mentioned that event y will be indicated by individual symbol occurrences of yj, and event x will be indicated by individual event occurrences as xi. And it is identical to the information provided by the occurrence of event x equal to xi about the event y equal to yj. That means we want to derive the equation for I of xi semicolon yj is equal to I of yj semicolon xi. Now how it is obtained? So we are going to check out that. Let's see that here we are starting with I of xj comma xi comma yj, which equation we have stated like this, that is hx minus h of x divided by y. And we all know hx equation is what? Px log of px, that summation sign, minus, here if I am going to take this entropy will be written as p of xy, that means joint probability, log of p of x by y. And because of that, now here in this next equation, the two logarithm functions subtraction we were having, so they will be operated in the numerator and denominator when the log function will be removed from that. So we are getting here p of xi by yj divided by p of xi, because we are going to get the values as the initial uncertainty minus the final uncertainty, and final uncertainty should be in numerator in that case for getting the minus value to be removed from the equation. And here this conditional entropy and this marginal entropy in the denominator, we are going to multiply and divide this whole ratio with p of yj. Now if we are observing in the numerator part, we are seeing that the conditional probability is multiplied with marginal probability, and this I can replace with the joint probability, and in the denominator the two separate marginal probabilities will exist. But now what I am going to associate is here for this particular case, we are going to have the representation for this joint probability as P of yj divided by xi into P of xi, because this multiplication also will result into the joint probability value. The denominator we are keeping as it is. So if I am replacing now this P of yj divided by xi as it is, and P of xi will get cancelled with this P of xi. So in denominator only P of yj will remain. And this equation is nothing but the mutual information of the receiver when seen from the transmitter end. That is, it is I of yj semicolon xi. So in this way, by substituting the value of marginal probabilities and the conditional probabilities in form of a joint probability, and by doing some rearrangements, we can derive the mutual information from transmitter end is always equal to the mutual information at the receiving end. And that's why this is said to be the transferred information. And that transferred information is either from transmitter towards receiver or from receiver towards the transmitter. So the same thing again here in the form of hx and h of x by y equation we have derived. So I of xy, which is said to be mutual information. As mutual information, two different events are existing. So for corresponding to two different events, two different summation signs will be carried out. For the two different events, two separate subscriptions are there of I and j. So that will be varying from 1 to n and 1 to m correspondingly. Here, the probability, which is joint probability for both of the events, has to exist. With that, the multiplication of the information, mutual information associated with xi and yj has to be taken. But now we are interested in average mutual information, and that's why to the mutual information we are multiplying with the joint probability of that events. Now, this mutual information can be replaced by log of this P of xi yj divided by P of xi into P of yj. In this case, in the next step, what we are going to do is, we are going to take this log of P of xi yj divided by this P of xi and this P of yj separately. Because when I'm taking log to this equation, what is going to happen is log of P of xi yj, which can be replaced by putting the value in terms of conditional probability and marginal probability. That is P of xi by yj multiplied with P of yj. While in the denominator here I am having P of xi, log is taken for that P of xi, but it is in denominator, so minus sign is associated with it. Similarly, for this P of yj, it is in denominator, log term is associated with it, but as it was in denominator, minus sign has to be associated with it. And here this P of xi yj, which was joint probability, that we have replaced with the multiplication of conditional probability with the joint probability. And again, this log term is associated with it. So what will happen? These two log terms are in multiplication, so I can expand them as log of P of xi divided by yj plus log of P of yj. So after the expansion, this log of P of yj term will get cancelled with this minus of log of P of yj term. So in the bracket, what is remaining now? Log of P of xi by yj minus this log of P of xi. See here, what we have done is in the numerator you are having joint probability. Okay. And joint probability we can represent as multiplication of conditional probability and that marginal probability. Up to this, is it clear? Up to this, is it clear?
Yes.
Okay. Then what we have done is we have applied the log function on this probability multiplication. So the log function when distributed on multiplication, it will be nothing but addition. That is log of, if I am saying log of a multiplied with b is there, I have to extend that as log of a plus log of b. With that same rule, here what will happen is log of p of xi divided by yj plus log of p of yj will exist for this whole bracket. Is it understood
मॅम
now?
मग कंडिशनल प्रोबॅबिलिटी घेताना फक्त आपण लॉग लॉग ऑफ पी ऑफ वाय जेच का घेतलं मग एक्स ऑफ एक्स जे पण घेता आलंच ना.
Please see, for this particular joint probability, we have written the conditional probability in this way. And if you are putting this as p of yj divided by xi, here you have to multiply that with p of xi. And that you have to do if I have to get the derivation as like this: I of xy is equal to h of y minus h of y by. Here what is our aim is we want to give the average mutual information in terms of these entropies. We are going in reverse way. First I have presented you the equation and now we are going for that equation derivation. Are you understanding?
Yes.
First I have presented this equation to you, that is hx minus h of x by y, because I want to tell you the definition for mutual information. And mutual information tells us it is what? The subtraction of initial uncertainty and the final uncertainty. So with relation with transmitter, initial uncertainty will be given by hx and final uncertainty will be given by this conditional entropy of h of x by y. In the same way, if I am looking for the receiver, the initial uncertainty associated with the receiver will be given by h of y and the final uncertainty will be seen at the transmitter and that will be given by conditional entropy of h of y by x. So in presenting the definition, I have given you this equation and now here we are observing that that derivation is validated with the help of these two equations. Cleared now? Is it understood?
Yes.
Okay.
Yes,
So if suppose I have to go for this equation derivation, so here in this bracket, instead of this p of xi by yj multiplied with p of yj, you have to put here p of yj divided by xi multiplied with p of xi. When I will do this, again in that case what happens, p of xi will get cancelled with p of xi and your remaining part will be p of yj divided by xi minus here p of yj. In that case, if I am substituting here in the bracket in the reverse way. Have you understood? Have you understood?
yes.
Hello? Okay.
Yes,
So
ma'am.
this cancelling is cleared now with the rule of log of AB is equal to log of A plus log of B. Is it understood?
Yes.
So here what is remaining? Log of P of xi divided by P of divided by yj minus this log of P of xi. Now on this bracket we are going to distribute this two summation signs with the joint probability. So it will be written for this first log function. Similarly, it will be presented for this second log function. But we know that for entropy equation to be written, if this log function probability is in numerator, it should be associated with minus sign. And here for this log of P of xi, we are having that association. So we are taking this out. We are taking this out. And that will be with only one probability associated with it. So its index should be varied for I only, as X is associated with I, and this whole summation will give me the Hx value. In the same way, when I will distribute over this, here I can find this is an equation for the h of x by y. But please note that here plus sign is there, and for original h of x by y equation, it should be associated with minus sign. So here we are putting minus of that. So don't get confused for putting this minus sign over here, because in original entropy equation, it should be associated with minus, but here it is plus is present, and that's why here instead of plus h of xy, we have to write here minus of h of x by y. So the next concept we are going to see after the mutual information is the channel capacity. So up till now, you might have understood that first for the transmitter, two parameters we have seen, that is information, entropy. Then we have gone for the mutual information, which is the measure of the information uncertainty transmission from the transmitter to the receiver, and that is related to channel. So again, related to the channel itself, one another parameter we have to study, and that parameter is named as channel capacity. So channel capacity will be always representing the maximum amount of information which a channel can transmit per second. So it is a measure of amount of information transmitted by the channel per second. So again, the unit for the channel capacity will be what? Number of bits per second, because information measure is in terms of bits per second. I was telling that for the channel capacity, it is nothing but the amount of information transmitted by the channel per second. And to achieve this rate of transmission, information should be processed properly or coded in efficient manner. Why coding is needed? Because we should not have any of the error to be occurred in the information to be transmitted. And if coding is not proper, definitely the error will occur in the information, and the maximum amount of information transmission will not be possible. And that's why we are saying, to get the maximum rate of transmission, always information should be processed properly or with the efficient manner. Now we will go for the mathematical representation for channel capacity. And as we have said, it is going to give the measure of amount of information transmitted per second. But we are saying that information should be in coded form. So coded form means, in our source coding, we have seen that every level will be encoded in form of some groups of bits to be formed, and those group of bits we are calling as symbol. And that's why here the channel capacity can be also termed in terms of the number of bits transmitted per symbol, because based on that, the number of bits information transmitted per second can be seen. If I am saying that a channel is able to transmit 100 number of symbols per second, and each of the symbol is consisting of 3 bits, then I can say that the channel is going to transmit 100 symbol into 3 bits per symbol, which is giving you 300 bits value. So 300 bits per second transmission. And so here, instead of bits per second, the channel capacity can be also termed in terms of bits per symbol. Because based on the bits per symbol, how many it is going to transmit, based on that also the channel capacity can be defined. So the channel capacity definition per symbol has been presented with this mathematical equation. And this mathematical equation terms for the discrete memoryless channel. For any discrete memoryless channel, the channel capacity is equal to maximum of trans information obtained. And trans information obtained is nothing but the mutual information obtained from the transmitter towards the receiver. So channel capacity is always expressed as maximum value of mutual information from transmitter towards the receiver. And this maximum value of trans information is possible over all possible input probability distributions for the X variable. That means corresponding to each of the symbol which has got transmitted and its associated probability. Based on that, here maximization of mutual information is going to happen. So to get the channel capacity per second, we are saying that the transmitter is capable of transmitting R number of symbols per second. Then maximum rate of transmission of information per second will be given by R into CS. And this is the channel capacity per second, and it will be denoted by C is equal to R into CS, where CS will indicate the channel capacity associated with per symbol, and this CS will be given by maximum of trans information obtained from transmitter towards receiver, while the channel is capable of getting R number of symbols per second from the transmitter. So with that maximum of transmit information possible on the channel, we have to multiply how many number of symbols that channel is capable to transmit. And that's why here R is multiplied with this CS, because CS is going to tell us the channel capacity associated with per symbol. So to obtain the ultimate channel capacity, we have to multiply the bit rate or transmitter rate with the channel capacity per symbol. And its unit will be now become as bits per second, while the channel capacity per symbol will have unit as bits per symbol. So you can now differentiate, because R is going to tell us how many number of symbols, but symbols are nothing but number of bits. So R unit is symbols per second. So ultimately it is bits per second, and that's why here unit of C will be bits per second. Now we have seen the different types of channels. So corresponding to every type of channel, the channel capacity value is going to vary, because corresponding to every channel, the initial uncertainty value and the final uncertainty value is going to vary. And we know that the mutual information is nothing but subtraction of final uncertainty from the initial uncertainty. So one by one, for the different channels, the channel capacity value we are going to check out. So in exam, there may be possibility that you have to write a short note on the channel. So in last lecture, we have seen the types of channel, wherein we have represented the channels with the help of the straight line representation with the number of transmitted and received symbols. Then we have written the channel matrix for getting the information to be transmitted corresponding to each of the channel. And here in this part, after the channel capacity definition, corresponding to each of the channel, the value of channel capacity we are going to mention. So if the question is asked related to any channel, you have to write its meaning of the channel representation with the straight line, number of transmitted and received symbols associated with that type of channel. After that, the channel matrix you have to represent, and finally the channel capacity associated with the individual channel, which we are going to cover now, that you have to mention in the answer. First, we will see the channel capacity associated with the lossless channel. So in lossless channel, what we were having? Every transmitted symbol will be possibly received by only possible symbol. There is no any path which is corresponding from one transmitted symbol to all other possible symbols. And that's why x1 will be received only as a y1, x2 will be received only as y2, and as like that the channel representation we have seen in lossless channel. And if such like this condition is there, obviously the conditional entropy value for such lossless channel will always become equal to 0. And if h of x by y value is 0, then the mutual information I of xy, which was to be obtained as hx minus h of x by y, will become equal to simply h of x. That means the mutual information is equal to initial uncertainty only, because here in the lossless channel, the conditional entropy, which was the final uncertainty, that is not going to exist. And that's why mutual information in this situation will be only the initial uncertainty with the value of h of x. And because of that, here in the equation of channel capacity per symbol, we will find max of hx only. And max of hx will be related with log to the base 2 with the number of symbols of that transmitter from transmitter which are going to be generated, which comes out to be as log to the base 2 for m value. So m is nothing but possible number of symbols transmitted from the transmitter. But in case of the deterministic channel, we are having h of y by x is equal to 0. Why h of y by x is equal to 0? Because in this situation, we are finding out all the probabilities associated with p of xi. But in the deterministic channel, we cannot find out that h of y by x, that is first transmission and then the reception, is to be observed. And so here I of xy, that is mutual information in case of deterministic channel, will come out as h of y. And because of that, here the channel capacity per symbol will come out as maximum of h of y value, which is nothing but log of n to the base 2. So for the deterministic channel, channel capacity per symbol will dependent upon how many number of received symbols we are having, while for the lossless channel, the channel capacity per symbol is associated with the number of transmitted symbols corresponding to that communication system. So these two channel capacities corresponding to lossless channel and deterministic channel you have to remember. The next case is for noiseless channel. So in noiseless channel, we are having both lossless and deterministic behavior which is going to exist. That means either any transmitted symbol I can see as a received symbol, or any received symbol can be transmitted possibly as any transmitted symbol. And that's why in that situation, the mutual information will be either equal to h of x, or it can be said to be h of y. And because of that, the channel capacity per symbol will come out as either as log of m to the base 2 or it will be log of n to the base 2. Now the remaining type of channel is the binary symmetric channel, and in binary symmetric channel we know only two possible transmitted symbol and two possible received symbol, and they will be with equal probabilities that can be transmitted or received. That means if I am saying 0 is transmitted and 0 is received with the probability of p, then 0 is transmitted but it can be received with the probability of 1 minus p, and vice versa case is also possible. And that's why here, for obtaining the h of y by x value, it should be p of log of p plus 1 minus p log of 1 minus p has to be done. So this value will indicate the h of x by y, but it is associated with minus, and originally here we want the subtraction, so this subtraction minus sign for the final uncertainty, and final uncertainty calculation minus sign will make here sign as plus, and that we can write as h of y plus this entropy equation for binary symmetric channel is going to give you the limit for channel capacity when we are having the presence of noisy channel, and that capacity limit has been put forth by the scientists named as Shannon and Hartley. So there are two different equations related with the channel capacity. One is derived for the channels which are noisy channels, and always the noisy channels consideration is with amount of white Gaussian noise to be added over the channel. It has been put forth by the scientists Shannon and Hartley. So it is also said to be the Shannon-Hartley theorem for noisy channel capacity. And one another theorem exists which works for noiseless channel, and that is given by only Shannon scientist. So it is named as Shannon's channel capacity theorem for noiseless channels. So these two theorems we are going to see in the next lecture with their derivation, and after that the numerical